Hello people, this is my third time recording this same stream. The first time, for some reason, nothing worked out. The second time I recorded for 30 minutes and my cloud VM just crashed, and so I had to rebuild that one. So what we're going to do in this stream is basically we're going to try to implement Monte Carlo tree search. I did finally figure out what we needed to do, what was the things that we needed to implement. People, I did it. And secondly, I'm going to show you my setup, and this can also be what happens when you're running this program or project for the first time. Something like this would happen. I have a new data set that I'm going to use. The first one used a simpler data set relatively. This one is bigger, better. So let's see what happens. Okay, so this is my vast.ai machine. It's a pretty good, pretty decent machine. And what we're going to do is we're going to start from scratch, basically how to run these things. I did check out some code from different people on how to actually run MCTS, but nothing seemed very impressive. Okay. First we need to clone this thing. So what you do is what git not found, pt install git, seriously. Yeah, continue on. Again, git not found. Git not found. Man, install git dash fix missing. Yes, continue. Oh, why is it downloading Perl? Okay, now it should work. Right, cd chess lm, you go here, and what we need to do is we need to open up download.py. We need to do a couple of modifications here. The first modification is, so we updated the new links, which is links 2000. The first dataset was actually downloaded from this website, which is pginventor.com/files.html. It has about 3 million games. I haven't checked what is the average elo rating or what is it. I just downloaded all these games. Most of these seem look like they are from big players. So for example, you have Ivan Chuk, you have Fischer, Bobby Fischer, you have Ivan Chuk. I'm not very good with chess, but my cousin is, and he tells me that these guys are pretty genius people. Ivan Chuk plays like crazy. I enjoy watching Ivan Chuk. And then but these are smaller size games. Most of the games actually come from openings and other different pieces. Now, what I did next was I downloaded all these games from downloaded these links from Fix Games database. What you have to do is there's no script. You actually have to go around and manually download, click this thing. So you go to January and download, and it gives you a certain link. You copy that link and paste it. So this is here. We need to start updating download.py. Okay, assets, links 2000.txt. all this is not needed. It's actually going to download this file, pbar.set description. You know what, let's just do this thing. No, I don't need any end calls. let it occupy the entire width. And yeah, so we'll need to manually unzip these files. This downloads a bz2 zip bz.bz2 file format. Oh, python download.py-d. Invalid. Oh my god, I fixed all these bugs, man. This one here and this one here. Okay. No module name import .wget pip install wget pip install chess. Okay, now this thing is supposed to work, but does it actually work? No moves.empty.json. okay, again m2id.json, we don't actually use that anymore. We use asset.moves.json, man. You move it. Make dir exist, okay, which is line number 131. This is not exists, okay, this is actually exist, okay. This should be downloading this file. Perfect. Oh, this is actually much faster than the other CPU system. You know what I'm going to do? I'm going to do a git status. I can't. Oh, cd chess. I add git add download.py and assets slash, and what do I get next? Is this okay? I do a git commit fix bugs, man, just that's it. And oh my god, are you kidding me? Okay, what you do is I have to add this thing. And the next thing I need to add is your name. What should I call myself? Call myself Doom baby. And I can, okay, now I can commit, I guess. Okay, git push ponde.yash97@gmail.com. oh my god. Perfect. Oh, this one is actually way faster than my other system. Can you hear the kids playing in the background? You know, I've actually shut my window since morning because these kids have nothing better to do than just play all day. These kids need to go back to school. Now we need to do other improvements, which is not all. This downloads this thing, which is .bz2 files. So these are all the files that are downloaded from PG and Mentor, and these are all the files that would have been downloaded from fix user.bz2 file. So we'll basically do the same thing. The difference being that we're going to use .bz2 here. All this is now goes into the bin, and we do a sub process .run. If you don't have bz2, go kill yourself. No, I shouldn't have said that, but okay. bzip2 -d, and you do f What is F? Okay, you have F. This is F. Ooh la la. Oh, this is fast, man. I like this. What exactly is fixed database? About. Welcome to the free internet chess server games database, world's largest chess database. It provides games played and relayed on free internet chess server, which is okay, freechess.org. The database gets updated in real time. You can retrieve and download games right after they are finished. When you're logged onto the fix, you can get access to database via GameBot. What is GameBot? GameBot started collecting all rated and unrated games played on Fix in October 2008, except Bughouse games and games. Ah shit, did I fuck up? Yeah, I'm not going to play all the variant games. These are all time controls and average rating. Okay, so this is basically standard Blitz Lightning. I have to get that. So this is free internet chess server. Over 3 lakh registered users. Register now. Beautiful picture of a woman. Download this. Okay. So, so in the last computer, I just had like 30 GB of memory storage, and what that did is it basically, as the files started expanding, I couldn't delete the rest of the files in time, and so it crashed. What is the file size of the downloaded system? It's du-hs data. Okay, it's about 1.3 GB. Yeah, unzipped, this would come close to 8 GB or something. Let's see. So bzip2-d data dot bz2. Now I think we should probably go into that folder and then cd data and then run this command. bzip2-d star.bz2. Now the good thing is that it actually deletes all the files that once it has extracted. So you'll see that the 2000 it still has the bz2, but it'll still remove the compressed files and only keep the unzipped files. Or does it? Is it actually doing that? I don't know. I do not know. Does it actually keep it? bzip2 -- help. A block sorting file compressor. Usage this. Pros. If invoked as this thing, default action is compressed. unzip2 default action is to decompress. bzcat is to decompress to std out. Are you kidding me? Why would you do that's? Yeah, if you have a very small file system, that would work. Okay, apparently it does not. Now let's start a notebook. We're going to manually assess all these files now. Just a minute. Alright, sorry for that. So what we need to do now is how it's still decompressing. You can see it's actually deleting the zip files as well. So it by default does that because if you pass it the -k flag, it does not delete the input files. So that means by default it would, because you now have a fast flag. Okay, so if I pass it the -p flag, it's going to go here. It's going to parse and save the data, like 36 MB files. Makes sense. When I actually wrote all this code, it was for my local machine. It does not have like 128 GB RAM as this particular machine does. This is done. Okay, so it's completed. Man, I'm scared. Should I run this thing? What is M? You know what? Let's not do it this way. You're going to use this. Glob import glob. pgn files is equal to glob all that is in data. Save all these files, which is equal to 31 files. Makes sense. Now what we need to do is we need to import chess and read one game. How do we actually read a game? The game reading happens game_game_self.read. Oh, okay. Encoding is Latin. I remember this because I used to have a lot of problem with this kind of thing. So let's open one small file, probably just for this month, and we'll figure out if there's some things that need to be improved in this particular code. So what we're going to do is pgn files. We take the one for this month, which is 2020. Yeah, this one would work. This is for January. You know what? Don't do that. Internet. Games, read this, and game count. Anyways, we have to do this entire process, which is pgn.read games. Pgn comes from chess import pgn. Okay. What is happening, man? Seriously? These kids! Go back to your schools, man. Yeah, it's good to have kids around. It's super boring when you don't have that kind of yelling in the evening. That's why you should do things in local machine, not on cloud. RE is not defined. Game count is not defined. I have 17,000 games just in for the January. Now you can kind of do a rough approximation, which is like cross 12 cross how many years is this, from 2020 all the way to 2001. That's about 19 years. Yeah, approximately 4 million. You have 4 million games of rating greater than 2000 elo, which means this is a very good data set. This is actually a very good data set. So what we're going to do is we're going to pump up the save after. We're going to probably just import this function right into this code. Okay, now it has to do something else as well. I can't remember what. So we need to somehow use the moves directly, and I don't actually want it to. What is this? M2 ID. Yeah, this is what I'm talking about. It needs to actually load this kind of thing. Do it here. JSON is not defined. Result is not this. Yes, I did mean this. Why is this? Why do I get this? Oh. Interesting. So whenever I'm comparing strings, I should always do this, right? Parse and save data. I'll give it the pgn files, and I'm going to tell it that its buffer is, so the buffer I used here is 10 lakh, no, 1 lakh, yes, 1 lakh. I'll increase the buffer here to a larger number of sequences, exponentially more. Let's see. T range is not defined. Is tqdm import tqdm? Okay, cool. From tqdm import the range. Oh shit. Can't open because local variable cg is referenced for assignment. could not load game 0. So clearly fucked up. What we're going to do is we're going to go over the game string 0, okay, which is this game, and we're going to strip it. Oh yeah, baby, strip it. Okay. And we're going to do pgn dot read game. Your object has a read line. I need to import IO, and I think now this thing will actually work. Now because M2 ID is not. Are you kidding me, my mate? Are you kidding me, mate? Let's just do this IO dot string IO. We need to do this now. I have this game, which is this is not this. Makes sense? This. Now what? Can't open because results is not defined. Where is results? Where is results? Oh shit. Can't open because results is not defined. Where is results? You know what? Oh, here it is. Result, this is this. Okay. Which is going to be the first thing that we write here, which is this. We need to define what these results are. Go here, along with this. Let's see now. Why is my local computer actually crying? Man, paid a lot of money for you. You shouldn't be hanging the shit like this. You think we would actually be able to code up the MCTS today? Okay. How do I know if this is actually working or not? I have files p bar. Okay. You know what? Let's just do this thing one by one. Why is the buffer too large for it? No. The thing is 126 GB memory. It should load the entire thing into its own memory, man. 6.1 GB is not that much. du-hs dot 6.4 GB. As I said, 6.4 GB is not that much. Should be able to load this and should be able to eat this entire thing, man. Yeah, kill the kernel. How long do you think that these guys are going to come after kill the kernel and say that kill is not safe or a good word? We should not use kill. What now? Okay, so this thing is not working. Hbox, right? It's actually doing this because It's not pretty much. It's not pretty, man. Let's do one thing. I don't think I've done any change. I haven't done any change to this. But still. Let's just do this. Okay, F center of PID. There is no PID here. No longer use a PID. FCNTR. This is finally it's working. Okay. But let's get back to MCTS. This thing is going to take a lot of time. I really wanted to show you how the training actually works, but oh wait. I removed this, right? Yeah, that's correct. What I did once was that I actually stored the entire dataset with the BOS and EOS tokens. That was stupid. Okay, so this thing is going to take a lot of time. What we're going to do is we're going to go back to MCTS and start making our own MCTS algorithm work. So the way MCTS works, let me just back in a minute. I just need to close the door. The way MCTS actually works is that there are four parts to this algorithm. The first part is the selection, where we select based on what is the Q value of that particular function, Q value of that particular move. The Q value is again defined by the value function itself. And people, you should know your Q value backups and these kind of things. Okay. So this is how you define a Q value, and based on this and the bonus for that particular probability, you take this particular selection. You simply do an argmax and you go over this. You continue doing that all the time. Now at one point of time, how do you actually define what action do you have to what action do you take? Now if you're here, you define the action. The this particular probability, this comes from the p row, p pi, or whatever policy function that you have. In this case, they have like two different neural networks. It's super complicated, but they came back and now it's all a single neural network. So you have a policy network which defines the probabilities over all the legal actions. You take what is the best action and you expand on it. Now how do you actually evaluate? Now if you go up to a leaf L, up to a certain depth, you'll be able to figure out what was the result. If you reach that terminal state, you will know what is this particular reward, whether this is positive or negative. If you don't, then in this case reward is going to be 0, because you're using a board game and the reward is only obtained at the terminal step here. But if you do, you should be getting a reward whether you lost or won, and we should have this in a code, and according to that your value changes. Now this comes the backup. The backup means now once you have the entire Monte Carlo tree expanded, what you're going to do is you are going to back up those values and then select the best action from these things to play. The backup in this algorithm actually works differently in AlphaGo, but we are going to use the one they did applied in mu0. So the way this works is that this backup at each entry step t less than equal to L of the simulation, the rollout statistics are updated if it has lost NVL games. We assume that it has lost NVL games, and so we give it this thing. NVL is a forced virtual loss. The value is equal to -1, and so NRST and WRST discourages this virtual loss discourages other threads from simultaneously exploring the identical variation. I don't know what that is, but let's just take what it's saying. At the end of the simulation, okay. At the end of the simulation, the rollout statistics are updated backward pass through each step t less than equal to L, replacing the virtual losses by the outcome. So NR, this thing, and this thing is, you can see this is the number of moves that it has to take. So we assume that it has played NVL games. So even though it has lost, this is the actual count, and so we add it. And because it has lost, we need to reduce that kind of value from these. So W is the total action value that we have ever obtained in this state action. And so you increment or decrement based on what is the ZT. ZT again is either plus minus RST, plus minus 1 depending on who won, or 0 if the game was draw. Asynchronously, a separate backward pass is initiated when the evaluation of the leaf position SL completes. The output of the value network V theta SL is used to update value statistics in a second backward pass through this thing. And the way this works is, you can see while you're updating this, so these are the new values at the bottom of the leaf, and now you're going to go over the tree till the root, over the tree, up the tree. You're going to go up the tree and update it according to this particular rule. So I have visited this node 1, so plus 1, and whatever was the value that was obtained at this particular state. Now the overall evaluation of each state is weighted average of the Monte Carlo estimates. This thing, so this, what it does is, whatever is the value that I've ever received plus whatever is the number of times that I've actually come here, and virtual losses and the other backward pass, and these mixed together. Typically the weighing parameter lambda actually depends. Okay, another important thing, all updates are performed lock free. What that means is it's asynchronous, anything can happen anytime. It's useful when you have multi-threading kind of systems. What is lambda? Okay, so lambda is the mixing parameters. In AlphaGo they used it 0.5, but they do show what were the different lambdas that they use. Yeah. So depending on the different kind of policies, R is the rollout, V is the value, P is the policy. Depending on different networks, this is the mixing constants that were used. Now we are not going to use this particular value function. Instead, what we are going to do is we are going to use the one defined in mu0 paper, and also we are going to use this particular value of action and not just this one, just these two things. So in this paper what they do is they define what is the CPUCT. Again, that is equal to 5. I don't know how they came to that value, but where is it? Yeah, so the exploration constant is 5, but in mu0 they became wiser and they figured out what was the exact thing. So we are going to use this. We have already coded this thing, but the way we did it was incorrect, and we are going to code it correctly now. Can't open because none type object has no attribute headers. How many? So I print this thing. This thing can't open object because so this is just for one file. right? Yes, this is for 1.5, which means we are not losing any information. Cool, man, cool. What is it? Stop. See, it should have consumed this entire thing. We are stupid to actually make the buffer smaller. We should have made the buffer so large, and it would have worked just fine. It would have been fast enough as well. But I have a new problem now. Once I have the move, where do I keep them? Do I like put them on S3? I'll probably do that if you guys pay me some money. Alright, let's go this way. So what we're going to do is we're going to use this particular backup. Again, this is the discounted reward, bootstrapping reward. This depends on what is the result at L minus K step, and for this we perform this kind of an update. Now note, this is different from the one used here, which is super complicated, where we need to like store 5 different values for each node, the number of times this thing came, the probability of taking this, the total value that has been generated from this, the state it came from, and something else as well. So this is the Alpha 0 paper. This paper is not much of use. They simply demonstrate that whatever the improvements that they made in Alpha Go 0 can also be applied here as well. This thing. So the search algorithm actually in this case is storing 4 values, which is N, W, Q, P. So W is the total action value, Q is the mean action value, P is the prior probability of selecting that edge. Yeah, and one thing important is at the end of the search, AlphaGo 0 selects them. So what's happening is that you have done a lot of search, and so now you're going to select a policy based on whatever search that you have done. At the end of the search, AlphaGo 0 selects a move A to play in the root position as not proportional to its exponentiated visit count. So this is like the softmax, or it's not exactly softmax, but it depends on the frequency of taking this particular move and not on the actual value of the move, action value of the move. And if the value goes below minus 0.8, then you basically resign. So you know what, let's start coding now. It's been too long. It's been so long since we've been away from home. First thing we are going to do is we're going to add a resignation thing, because we know that was a problem in a lot of my runs. If value less than minus 0.8, move is equal to resign. Okay, and here we say that if move is equal to resign, then game is over. So let's just do it. If move is not equal to resign, we are going to do all these processes. Player has resigned. Now we're going to go over the Jupyter notebook, start coding here. So everything is going to be functional, because functional things are way better than class objective things. Class are super object oriented things. There's use of both, but if you're using object oriented programming too much, there's a good chance that you do not realize that you're overdoing things. Functional keeps you in line. You have a model, you have a root node, and you have a board B, which is basically on which board is the user supposed to play the action. Now you have the state, you have the S is equal to B dot move stack. Okay, so moves MVIDs is equal to vocab. I should probably make a function right now. I should probably make a function like this: def get move IDs, which takes the board, the vocab, and this would return vocab strx up to 4. I turned off tab 9, but for some reason the laptop is still pretty loud. Okay, so this function exists. What we'll do is we'll simply send it to the, that's it. Okay, we need to have this, and we need to pass it vocab as well. It processed like exactly 50,000 games before it found another issue. So these are 258,000. There's clearly more than 3 million games in this particular data set, which is good, because this is like a higher quality data set. And so in supervised learning, everybody knows that data is basically everything. Okay, moves. The first step is going to be the selection of what moves to play. Selection. Second is expansion. The third is where's the third? The third is evaluation, and the fourth is backup. Now if you think about it, selection and expansion are basically the same thing. What we're going to do is we are going to make a function called expand tree. What this function does is that it takes in the model, it takes in the node of this root node is not the same root node. Expand tree works much more like our generate tree function. Okay, expand tree works much like a generate tree function, where we call this thing again and again, and we expect it to actually generate the entire tree. Now, expand tree takes in this thing. The action to be taken is determined by the node values. So that means for what we're going to do is we're going to say root node dot update queue. This update queue is going to update only for this particular value, right? Yes, update queue, and then we say action is equal to sorted of root node dot children. The key is lambda x dot value. take whatever is the root node is the last, and action is equal to root so yeah, move is equal to action dot move. So what you're going to do is just do another thing, just this way. This is another move, is just a function, helper function from here. This returns a chess.move, and what it does is that we always force promote to queen. As you know that in our case we do not have the ability to distinguish between different promotions, so this is why we are going to use force promote all these things to q. It's going to take a couple of hours, man. I think so, at least. While I'm burning through my money. And I'm burning through my cash. Okay. Then I also need a board. What I then do is I do a B copy, which is board copy. Create a copy for this child. Now we do a B copy dot push move. No, I think we messed up somewhere. So right now the assumption is that root node has already been on the board, and we need to find the next best move. So the way this is actually going to work is that I need to actually get policy. Let's just use simpler terms. Get policy model input IDs is equal to the action that has to be taken is I need to add first to all the children. This is much like this particular function, the one step. So what it does is now we don't actually need all possible future probabilities here. What we need to see is that if we are given a tree, let's assume that we have been given something called tree. This is the MCTS tree for this move. The values, the leaf nodes basically are added to this, and the nodes are actually added to this particular tree. This tree, think of it like an external database where while all your operations are running, this is the main tree that you're actually updating. So what we're going to do is we are going to first define tree. Tree is none. Wow. So tree is none. This is the MCTS tree for this move, and the nodes are added to this. The way we can actually define it is, this is the node. What would you say? To define a root node, and my root node is actually the tree, right? That is how you would define it. Let's not pass. So if I have a root node, this is what eventually ends up becoming the tree, right? I don't know, we'll figure it out later. Now we don't actually need to not add to children, update visit count of children. What that means is we need to tell this model that how long have you been streaming? Yeah, it's almost 1 hour. Why? You know what? Let's first play with the blunt tree. Let's not assume that. Let's assume that the children are not yet known. So what we are going to do is we are going to add children to this thing. Add children. The move that we should be taking, if I have all these children, then of these children I would like to pick the child that has the highest probability of taking. Not as add a global tree here. Right now what you're going to do is you're going to simply say that update the Q values based on the root node, but for this I need to add the children. Oh my god, why am I so confused? God, why am I so confused? I need to remind what the legal moves of this board. The way I do it is simply copy pasting. Because why? Because I don't have brains. Okay. These are all the valid moves for this tree. Then what we do is we do a logits MVITs, and we perform LG, this is called logits, is equal to softmax of this thing. This is our policy. Now once you have the policy, what you're going to define is we need to add all these values to children. So what we're going to do is we have root node there is no top P or something like that. So what that means is For LGT, comma MV and zip MVITs, comma logits, comma MVITs. The value of this action being taken is this. Compiler to list. This is right. This is to list. What is the value of no, so the root node has already been played, so what I need to determine now is what are all the possible future moves. And so I take I feed it whatever has been played till now, and this should return me whatever can be played and what is the value of this state, of what is the prediction till now, right? So this tells me this particular feature, but this does not tell me what happens if I take all these future moves. I need to know if I take all of these legal moves, what is the value that I get. Assuming that the selection is already complete, what I do is I batch all the moves till now. I pass it to the model. For each move, what is the distribution of future moves? I do an expansion, which means I need to know. No, expansion depends on the children. Oh my god, why am I so confused? We did something wrong here, because now I have to run the policy 2 times, whereas in the first case I had to run this only one time. So what now we need to do is we need to batch. We need to take the policy of all these legal policies. I need to determine what is the best policy here. So for that I need a global tree. While I do not have the global tree, what I can do is I can actually create that kind of thing. Now for that I need to know for all the possible future moves that I can take, what is the value after taking that move. So I have the move IDs of all the possible future moves. Next what I can do is I'm going to batch this thing by the method I mentioned here. Move batched, and I'm going to run the whole process again. Long dot long. Now this thing I do not need. This basically tells me what are even further possible future. This is at k plus 2. If this is so what this loop is doing is that it is telling me all the future possibilities at k plus 1. I need to go and find what are the best move, what are the values for taking all legal actions at k plus 2. What that means is, for that I need to actually run the model to find the policies at k plus 2. Logits, we're going to call this thing logits k plus 2 kp2, and this is values at kp2. This is logits at kp1, and this is values at kp1. Logits at kp1, logits at kp1. These two things give me this thing. Now I have the prior probability with which what move I am going to take. Now this is a super horrible code I have written till now, but let's just go with this thing. So what that means is I have logits and I have at kp2, and what I'm going to do now is I have the value of taking this move, and I have the probability of taking move. Now the challenge is that my network actually predicts two things at a distance. It needs to see, it needs to have whatever move that you want, what only after you have played it can it actually predict what is the value of doing it. So the value here is going to be the value of taking this move. The move is going to be MV. The probability is probability of taking the move, and B is B. Is that so? No, B is not B because I have not pushed all these moves to B right now. So for that, what I need to do is I need to create a B copy, which is B dot copy. To do this thing down here, right? Okay, and this B copy is what goes in here. Money on my mind and my money on my mind. Still doing 2011 only. This is 438 games. 1000 games, sorry. Let's say I will be very smart if it can actually learn all these things. Going to be super smart. Okay, so now what I'm going to do is I'm going to say that update the Q values of this function. I'm going to sort it, and I'm going to take the action. I'm going to return the move basically. Okay, now how do I remove this piece, because this is duplicate? If I expand the tree, I do need to know what are the move IDs I will be playing on. So what I can do is I'm going to push this thing out here. This actually becomes my one step expand. This is my wrapper for it, which is expand tree. This takes in far more values, and if I just put this thing right here right now, this is not correct exactly, but still, just for now, I can just say one step expand model root node and B, and I can also give it the move IDs that I wanted to take. Yeah, move IDs is going to be this thing, and then I can, yeah, so this is going to return the best move for this board. Expand is going to take in the model, the root node, the board, and it's going to take in the depth, which is if not depth return. Okay, this takes in the depth. It's going to take the action that maximizes this particular value. Yes. Okay. And once I have that particular move, what I can do, B is equal to B copy. No, let's just B future is equal to B dot copy. This is selection, which is play the best move till now. Expansion, which is expand tree with model and root node B and depth -1. Alright. So the difficult thing that we're doing here right now is we're actually running this thing 2 times. We're actually running the model twice, which means it's going to take longer to run each epoch, which is not good. But I still have to do that, because in order to know, I need to find out what are the, so this assumption is gone. Root node at K is this thing, right? So if I have a root node at K, I need to run the model till K plus 2, because I need to know what are the values till K plus 2. Let's just go with this thing right now. There is no top prop moves anywhere. Nothing like that exists. The probability of taking this move. Wait, there is something wrong? No. Alright. There are 30 possible legal moves in this step. Now what is going to happen is that we're going to first we need to start by first defining what is the root node. The root node is node takes the value. Okay. I don't need the logics now. No, I do need the logics to define the probability. Probability value is actually, no, I don't need the logics here. I don't. There's no probability whatsoever, man. It's just value. I'm already told that this is the value. The move is equal to cab stir b dot move stack -1, whatever was the latest move that was made. Yeah, the p is the 0.0 because this was just taken, and p is okay. Int object is not subscriptable. So this is the move that we have taken. If we should probably, we should not do it like this. What we should actually do is we should assume that the game is starting from scratch, because this gives us a much better understanding of what is happening. We are going to start the game from scratch. SCRATCH. Okay. Alright. Okay. These are the moves. So this entire thing is now completely useless because there's nothing like this anymore. So you're going to start from scratch, which is moves is equal to 0. That's it. List object has no size. Tensor moves dot long. List index is out of range. You have values, and you have, oh my god, it's just saying 0.1. Should have said 0, but okay. And you have legal moves, sorry, logics 0, legal moves. Alright, just print plt.print and see. So it's super sure to make this particular move. The probability is 0.09. Wow. Oh, 0.9. Okay. Yeah, you do not have a move till now, you just have king. Okay. It's not, you know what, we should not do this. Move is game. The game has just started. What you're going to do is you're going to tell it to, expand tree. We send it the model, we send it the root node, we give it the board, that this is the board on which we are playing this game till now, and we give it the depth. We tell it that you just have to go till depth 2. Okay. Okay. I guess this is going to take like half a day, something like that. This is still at like 2011 only. The 2019 is completed and 2011 is completed. It's going to take a very, very long time. It's going to cost me a lot of money, apparently. Okay. So what we can do is no. We're going to complete. We are going to complete MCTS on today's stream. We have to do it. Okay. So expansion tree. This goes into the expand tree. Now what you're telling it is, if you have no depth, then you return. Okay. Otherwise, what you have to do is you have to look over all the possible futures, which it does. So right now we should get largest KB1 dot size and values KP1. Okay, let's get stuck here only. There is no moves. Get move IDs should consider, you moron, it should consider vocab game. That's what you're calling it, right? Okay. Yeah, game. Moron, you should consider this. Okay, so we'll have to run each network twice for each and every step, because we also need the value. Okay, this is horrible engineering, man. Okay, just delete this cell. Okay, int object is not callable. And I will call an int. There is no shape. Oh, brilliant. As tensor moves, there should actually be dot view 1 comma len moves. Get more IDs, and the second thing is going to be again the whole process of getting. So I can actually pass it. I can actually pass it. What are the legal moves? This way it doesn't have to keep on calculating that thing. So pass it the legal moves, and what I can do is tell it that you, my dear son, are the softmax of yourself, masked by legal moves. Sorry. Why is it doing like this? You know what, let's take a break of 5 minutes. I'm actually going to listen to music now. See, remember shit like this. This is why I don't like Google. It's going to keep on suggesting me MF Doom now and food for some reason. Wu-Tang Clan. Yeah, let's listen to Wu-Tang Clan. No. I know what I'm listen. Mathematics. Ah, sorry, not this guy. Most deaf. So let's get back to this. So if I do this, it actually works. But if I say too many indices for array is one dimensional but two were indexed. Oh shit, I'm actually looking at the wrong one. It's actually working. Okay. So I had to get the just 20 things. I had to get the value of it. Okay. So now what I need to do is I don't need to write this thing again. Neither do I need to do this thing. Now I'm going to tell it that let's just start logging effectively now. I'm going to pay off later. Depth we do largest kp1 dot shape and we do value kp1. Now this thing is working. Now I don't need to tell it what are the move IDs that it should take. I just need to give it what is this, but this is the root node and these are all the what I need for you is to update the root node and give me print len root node. Okay. Move IDs is not defined. Now you can see till now what the board we have. So board is complete. No move actually has been taken till now. In that case, move IDs is not defined. So we are going to send it all the possible move IDs it can take from here. Largest kp1 is not defined, so you can also send it the largest kp1 which comes from here. Float object is not retrievable. No man. I don't actually need whatever are the logics for this particular thing. Zero zero. The move IDs maybe 0. Oh yeah. No. Oh, so these are wrong move IDs. We need to actually send it what are the legal moves. Yeah. Now we're talking. Okay. So this becomes to list, and now it's going to work properly. Okay, cool. We're going to need a len this thing. And we need to delete this because we don't need it, and we don't need this thing either. Okay. Now int object is not subscriptable. What we are sending this thing? The move mv is inv vocab this thing. Expand tree is missing the positional argument move, so I'm just send it this. And should I actually send this the legal moves? I mean, it's smart enough to determine this right from here. I don't need to send it the legal moves. So I can just do this. I can remove this piece, and I need to send depth here. Whatever the move IDs are, the possible future moves that it has to take. Yeah. Cool. Let's see. Unsupported string passed to list. Unsupported string passed to list format. What does it move? The value? Oh, so the value is this thing. No, it works. Perfect. Oh my god. Okay. If I do depth is equal to 2, still adding to the root node. I need to redefine the root node now. Best move, but not just that. I want the best root, best node, the next best node. This is the best node. This is the move, and I need to send it the child move, child node to take, and I need to pass it this thing. It's still not doing that. Depth of 2, depth of 1, and 0. Print length root node. Okay, I told you this thing is going to pay dividends later. What we need to do is we're going to print this thing correctly. We're also going to tell it we don't need any of this now because the shapes are pretty much sure. Root node dot s. We need to know what string this object is. What is it going? Okay, so it's taking f4 to 5, f2 f4, and then it's taking c7 c5, c7 c6. Where is it? Okay, here's this. Now this is getting added to game, but we actually don't want that. It should get added to it should be added to the child node. Yeah. I really wanted to show you guys the training piece of it. What I'll do is I'll make a small clip, probably upload it on my Instagram, or take it from my phone and upload it on YouTube. How it actually trains. Span tree. Let's just make the nomenclature a little bit better. B and model is equal to model, root node is equal to root node, B is equal to B, largest kp1 is equal to largest kp1. Positional argument. Best move for this board got an unexpected argument. Root node. What do you do have? Root node K. Oh shit. That's why you don't behave like a stupid fuck. Now it's gonna be right. Perfect. What that means is it saw the game. It took F to F4 and then it took C7 C6 and after C7 C6 the best move that it found was D2 D3, right? Okay people, we are going somewhere. Not good place, somewhere. We're going to add this is very small. If we and we is equal to false if we and we is equal to cool. Oh my god. Now what is going to happen here is that when it actually takes this thing, it is an update Q value, which means for the first time it is going to take this particular action, and from the next time in the next simulation it is going to take different action. So what we're going to do is we're going to complete till backup. We're going to do an evaluation. How much depth, how much time does it take if I choose depth 10? Oh, it's actually pretty fast. Damn. Root node dot total children. What is the total nodes? Also, we just evaluated 304 different nodes. If I take it to depth 100, does it crash somewhere? Let's just take it to depth 10. 10. I never understood these magic functions. This is too complicated to use. And the computer goes brrrr. You can see, you can hear it. Yeah, you can. Got 20 depths, which means it has analyzed 2,119 different moves. Okay, people. Okay, I think we are getting somewhere. If I do 30 depths. Takes 5.70 seconds. It has analyzed over 2,886 nodes. So now we are actually getting this. Actually, policy works that where we're actually able to see 1,000 nodes per second kind of performance. Somewhere around that. Now, what the next thing we're going to do, and after which I think we'll end the stream, is that we're going to upload. We're going to merge these two things into our main code base. And see what happens. One step, one future. It's that person thing. there's this thing. I need to pass it vocab and inverse vocab. I'll do that later. Let's do an expand tree, which means I'll expand it like this. Now one thing I do need to define is we should probably push this thing down here. Let all the torch things be together. From torch import our tensor. We don't need functional because in a way we do perform softmax through numpy or manual way. We don't actually need to do that. So now I also need to pass it two things, vocab and inverse vocab. Again, what I do, oh shit, what I need to do is I need to pass it to this thing. Yeah, now it makes much more sense. And I also need to pass it here. Vocab is equal to vocab, inverse vocab is equal to inverse vocab. It expands the tree, and what we basically say it, continue the expansion, continue the expanse. It's not depth, return. That's not a good way to actually write it. We're going to say if depth greater than 1, expand. Otherwise, if the depth is already 0, we don't even need to expand it, and this way we can get the best performance. Now all we have to do is we need to perform a backup to find what is actually the best move to take. Now we have the expansion. Now we need to perform backup. MCTS backup model. So the way evaluation, now we need to add evaluation first, because we need to know what are the values for terminal states, and the evaluation is actually going to happen here. So we are going to say if b copy dot game.py game. Is there some easier way to determine if it's a draw? Chess.com, no, chess, Python chess. Yes, this is what we need. We need to determine if this is a draw. Can claim draw. Okay, so this is like the largest thing. Basically tells it that without running the whole thing, you can simply can claim draw, then value is equal to 0. elif b copy we also need to determine who won. So if b copy is stalemate, is game over, can claim 50 moves, etc, etc, etc. Win, checkmate. Board dot is checkmate. If board dot is checkmate, value is equal to 1 if same player else -1 else value is equal to this thing. Simple. And in either of these cases, we don't need to update the node. What we need to do is we need to set it like this. root node dot children is an empty list. Not like that. Value is equal to value. Because this game was drawn, you don't have any more value, and otherwise you need to expand it. See, what we have written here is if this is the check for terminal state. States, because there can be more than one terminal states. If this is not a terminal state, then oh wait, I think I fucked up. This is not where you actually add. This is not where you check this thing. This is the wrong place to check it. Place where you need to check it is where you actually push the move. Let's what let it be. If now you can basically copy paste this thing. Root node value is equal to this. Else do this. This makes much more sense. What we'll do from here is that we'll copy the flags. In these kind of things, that evaluation etc., this is going to happen here. This is where basically the evaluation place, right? And now we need to determine who is the player. Oh shit, we also need to add color. Is this going to be a racist thing, man? Oh man, color, anti-color, inverse color. Yeah, let's call it color and inverse color. So we need to find color here. We need to define it as white, and the color here will be root node dot inv color. Do you guys understand why we're actually doing this? We need to do this because we need to determine what actually happens, right? What I'm going to say here is now the value was 1 or -1 actually depends on the root color, not just the color, the root color. That means I need to have something else called the self dot root color. This is going to be the color. No. colors help in determining the value in terminal conditions. Alright, so RC is, we're going to define RC as white, and otherwise RC is always going to be root node.rc. Oh, else there's an issue here. Yeah, we don't do any of this shit now. Expand tree. Expand tree requires two positional arguments, cap and inverse for cap. Init. Oh, sorry Mike. B copy is not defined because this is not B copy, this is B future. Same player is if this is basically child node to take dot color is equal to RC. Just take depth of 10. Should we improve the print statement? Let's not do that. That's too much of a headache right now. We should probably have a separate function which is print tree. Now it would be able to print much better tree than this. Yeah. Evaluation. This is selection. No, this is selection. God damn it, man. This is selection. This is evaluation. This here is expansion. No, this is not the expansion. This is expansion. Man, this is good. This is actually very good because in my whole life I've never actually been able to get into so much detail and depth of things. Streaming is good. I think I'm going to continue it for some time. This is a good habit. This also ensures that I keep working, because usually I have a habit of losing focus, but not right now. I'm on a roll, people. Okay, backup. A root node. So the way backup is going to work is we're going to use the this particular formula, which is this thing. For that we're going to do this. Okay. I know what to do. I'm a genius. No, I'm not. Root node dot get get selection values. So what we need to actually identify is through only the actions that we have taken. Okay, this is tricky. What we actually need to do is through all the actions that we have actually taken, we need to child node to take. Is there some way we can set? We have a flag. So there's just too many flags right now. We should probably fix this. Okay. Now what this flag is telling me is that have I actually chosen this particular have I actually chosen this child node to find or expand the tree? No. As I'm going down the tree, and what I'm actually going to switch on the camera and try to explain. Alright. I don't want to come into picture. Alright. So you can see here that if I have a tree like this, it's going down one by one, and what I need to know is what are the exact values of these nodes that were expanded. I don't need the values of all of them because the backup is going to be performed on the values that were chosen. So how do we do it? Do we keep a live dictionary of all the children that were chosen? That would mean something like a rolling list of children. Rolling notes taken, notes taken. Why is it not printing out the logs? And brrr goes my laptop. What? This analyze 2000 positions? Okay, this is a bug here, and because it did not fall into the infinite loop, these checks actually work. Oh, these checks work. It actually, we just find out. I also need to figure out why this print is not, it's not logging. My goodness. Okay, people. Now we're in business. Now we're talking. Now, oh fuck. How's each node talking? Because each node, technically, the first node append. Okay. So F2, F4 is the first node that was taken, so on and so forth. Right. So if I can just, so we can actually see it like this. That for this thing, this was the well taken. For this thing, this was the well taken. This was the well taken. Okay. I'll be back in 1 minute, and you're going to be. And we're going to finish Monte Carlo tree search today. Boys, we are going to finish Monte Carlo tree search today. Even if it is super hacky and it does not work all the time, we are going to finish it. Now I do know what are the nodes taken. So what the backup means is I actually don't need what are the nodes taken. Now this is how it works. Def backup is I need what are the nodes taken list. Because I know that this is in which order this was taken. Now I also need a discount factor, which is going to be 0.99, and for n in nodes, for I comma n in nodes taken, enumerate nodes taken, but do I need to go to the last one, because the last one's value is always going to be the same. So for I comma 1 in enumerate nodes, for j in range this node update values. So for j in range, no, I don't even need j now. For n2 in nodes, goddammit, nodes taken I from up to -1, because no, in this case I would need the -1. This node values dot append n2 dot values dot value, yeah, it's dot value and n dot value is equal to the this formula. First we need to extend what is the cumulative discount reward. Bootstrap value is equal to discount factor. No. So discount factor is bootstrap value is what is the immediate reward, which is R1 plus gamma R2 plus gamma squared R2 R3 G1 R2 into g squared r3 into g cubed into r4 and this underscore. So what that means is for j, I can just add it here as well. Don't even need to have something here. This node, so automatically my bootstrap, I can define my bootstrap here 0. Yeah, bootstrap boys, bootstrap. I'm thinking I'm going to watch a movie today. Bootstrap plus equal to discount factor to the power j minus 1, because for 0 it is going to be 0, which is 1, so this is incorrect. Oh god damn it, no, it's correct. Bootstrap is equal to discount to the power this, to the power j times the n2 dot value. And so this is done now. All I have to do is I take n dot value is equal to n times the bootstrap value, no, n times the current n dot value plus bootstrap value n dot n, this is n dot value divided by n dot n plus 1 n dot n is equal to n dot n plus 1. Does it work? Let's see. Yeah, we did it. Nice. So you can now see how the values have actually changed, and I think we just implemented Monte Carlo tree search. Nice. It's almost 2:19. What I'm going to do is I'm going to plug this into my main code base, and then I'm going to close my laptop and go and have some dinner. But right, we just implemented Monte Carlo tree search, and so this is not the complete Monte Carlo, because right now we are just going over the only a single node. Basically what you need to do, this is just one simulation. So next time tomorrow what we're going to do is we're going to expand it to more than one simulations, and say thousands of them, and so then you'll see the actual improvements that have start coming here. So for that we need to do two things. First is figure out how to actually run 1,000 different simulations effectively, if possible parallelly, and second, we need to have a global tree that is going to go into each and every that is going to add to each and every tree, basically. No, that's going to go into each simulation, and that tree is going to get updated in each simulation. Okay, so we did it, boys. See you next time.